This is chapter 23, electromagnetic induction. And we've already learned that a current carrying wire is going to be subject to a force if the current passes through a magnetic field. But it also works the other way. And this was Michael Faraday's brilliant intuition. He reasoned that if electricity produces magnetism, then magnetism could possibly also produce electricity. And indeed, that's what happens. And the reason it happens, as we can see in this image here, is if you have a current carrying wire or just a conductor and you don't have it hooked up to a battery or a generator or anything, you just have it hooked up to a galvanometer like we see here. A galvanometer is like a voltmeter, but it gives you both positive and negative readings. If you hook up this conductor to a galvanometer and you simply give it a velocity, either up or down, what you're doing is you're moving the stationary charges through a magnetic field, meaning that because of the right-hand force rule, those charges are now going to be subject to a force themselves. And the charges will be propagated along the wire in the form of a current. And that's shown in the deflection of the galvanometer needle. So there are really two sides of the same coin, electricity and magnetism. And we can also see that it works both ways. As we're going to learn this lesson, it's the cutting of magnetic field lines. We can imagine magnetic field lines between the north pole and the south pole of this magnet. We have two magnets here, but the north pole of one is facing the south pole of the other. And when charges cut through magnetic field lines, they then become subject to the right-hand force rule.
We can apply the right-hand rule. All right, so we know the right-hand force rule. If you line up your thumb in the direction of the charge's path, in this case where we're talking about positive charges, just because that's conventional current. So we have the thumb lining up with the path of the positive charge, and our fingers line up with the magnetic field lines. Well, then the palm of the right hand faces in the direction of the force that those charges in the wire experience when the wire is moved. And that force is precisely what pushes them in one direction, and that's a current. When you have charges moving along a wire, you have a current. So you could say the right-hand force rule is really the key to understanding electromagnetic induction. And we apply the right-hand force rule because the magnetic field lines are being cut by a conductor that contains charges. And since we're giving those charges a motion in the field, those charges are forced to move. And that forced movement is the induced current. Now, induced electromotive force is another way to talk about it. When we talk about induced current or induced electromotive force, we're really talking about the same thing, even though electromotive force, the units are volts, and current, the units are amps. So they're not exactly the same thing, but the cause of induced EMF is the same as the cause of induced current. It's the same exact phenomenon, really, just a different way of looking at it. So let's take a look at these three situations here. On the left, top left, I have a bar magnet, and these blurry lines to the left of the south pole indicate that the bar magnet is moving towards the right. Well, since that bar magnet is moving towards the right, its field lines, and we can draw field lines. I'll do that right now. Draw some field lines that extend out even more, like up here, and then we can draw it out here, right? You can see that as we move the magnet towards the right, the conducting loop, so this coil of wire here, is going to be cutting magnetic field lines. And whenever you have magnetic field lines cutting a conductor, or rather a conductor cutting through them, you're going to get induced current. Similar situation happens here on the top right. Here we have the magnet going to the left. And so if I draw more field lines, okay, it's just a rough drawing, but just to visualize it a little bit. If I draw more field lines, you can see that, again, although we're going in the opposite direction here, the conductor is cutting field lines, and that's why we're getting induced current. And finally, the situation down here on the bottom is we have the magnet stationary, the conductor stationary, and there is absolutely no current because there's no cutting of field lines. Now, granted, there are some field lines that we can extend out, and so I'll do that now. Extend some field lines out. And so certainly in the vicinity of the magnet, there are field lines that that are within the loop, right? But they're stationary. Therefore, the coil, this conducting coil, is not cutting through magnetic field lines. It's just staying still. And you need to have the cutting of lines with the motion of either the magnet or the coil or both in order to get an induced current. So what we have here is a situation similar to the one we saw on the last slide. We've got a conducting coil, we have a magnet, and as you can see when they're both motionless, there's no current. All right, what happens if we move the magnet? Well, if I move the magnet, whether to the right or to the left, in the vicinity of the coil, I have motion, and that motion means that magnetic field lines are being cut, and therefore we have an induced current for the very same right-hand force rule that we talked about at the beginning of this video. All right, now if I move this slowly, you can see it's not a whole lot of light from that bulb, but if I move it fast, back and forth, I can see I'm getting a lot more light. As we're going to see, the speed at which these magnetic field lines are cut, that makes a difference in the induced current. Now, another thing that makes a difference in the induced current is the number of loops in the coil. And so right now I have 2 loops. Let's increase that to 4. Well, I guess this one will just do to 3. And notice how I'm getting a brighter light as I move the magnet back and forth. And you can see that the current is getting induced because of this rapid cutting of magnetic field lines. Now let's suppose I increase the area of the loop. That also gives me a greater effect. All right, now we're going to talk more about this phenomenon and try to explain it or understand it a little bit better, but I thought that this animation could help us to visualize things at least a little bit better. All right, I wanted to introduce the concept of magnetic flux because magnetic flux is going to be important for our understanding of electromagnetic induction. So first let's talk about magnetic flux in terms of an analogy, and that analogy is rainfall. Let's suppose we put a pan out to collect rainfall. Well, if we have heavy rainfall, that's more flux. Flux just means flow, that's all flux means in Latin is flow. So what we're talking about is flow. Just as a lot of water, a big volume of water flowing through a hose is a big flow, well, a small volume of water flowing through a hose is a small flow. Same type of concept. If we have a heavy rainfall, we have a lot of flux. Let's suppose in the middle situation, we have just as heavy a rainfall, but because of wind, it's slanted, and therefore the flux is going to be lesser than in the first case. So the tub will fill slower. Now in this third situation here, We've got vertical rain, which is the ideal orientation. There's no slant, no angle at all. It's just purely vertical. However, it's a weak rainfall, and so that's less flux. All right, so flux then, when we're talking about rain, depends on the angle between the container and the flow, and it also depends on the intensity of flow. All this to help us understand magnetic flux, because magnetic flux works the same way. So these red arrows are magnetic field vectors. Okay, so these are arrows on magnetic field lines. And so let's take a look at each of these characteristics. All right, so flux is proportional to the density of flow. If you have denser field lines, you've got more flux. Flux varies by how the boundary faces the direction of flow. So if the loop is at an angle, there will be less flux than if the loop is the area of the loop is perpendicular to the magnetic field lines. All right, that makes sense. Kind of like the water of the rain analogy. Slanted rain means less flux. And finally, flux is proportional to the area within the boundary. So you got a small area, that's small flux. If you have a big area, that's big flux. Now it's time for a little historical background.
In commerce and chemistry alike, few things have ever remained the same for long. And even as coal was gathering steam in the industrialized nations, a new and different element entered the picture. It was called electricity. Nowhere was it more hotly pursued than at the Royal Institution in London. And no one had pursued it more closely than the 18th century's most diligent and intuitive scientist, Michael Faraday. He probed the mysteries of science because, for him, the building blocks of nature had been created with a fundamental unity. And Mr. Faraday believed that the blueprint was to be found within the laws of physics. With that belief, Faraday was motivated to unearth a new link between two of Mother Nature's fundamental forces, magnetism and electricity. His quest began in 1821 with Hans Christian Ørsted's discovery that the flow of an electric current creates a magnetic field. First, Faraday reproduced the experiment, and then in a roundabout way, he took a major step forward. He invented a device that kept twisting as it followed the circular magnetic field created by a current. And from this point onward, when people thought of things turning to create power, they no longer thought of windmills and steam engines alone. With this amazing device, an electric current could create physical work. In other words, this was the world's first electric motor. But Faraday's restless mind saw more than circles of magnetic force in Ørsted's discovery. He saw a crucial scientific question. If an electric current could create a magnetic field, could a magnetic field create an electric current? The answer didn't come easily. It took lamp oil and paper, brilliance and tenacity, untold combinations of coils, magnets, and wires. It took more than a decade, which is why biographers note his legendary patience. But in 1831, Michael Faraday had the answer. As he connected a battery to one coil, current flowed briefly in another coil. He'd found the answer, and in the process he'd discovered the principle of electromagnetic induction. how does electromagnetic induction really work? In other words, how can a magnetic field drive an electric current around a circuit? Magnetic fields apply forces to electric charges, but only if the charges are in motion. The direction of the force is perpendicular to the velocity and the field, and depends on the sign of the charge, in this case, negative.
Please note, the right-hand force rule applies to positive charges and conventional current. For negative charges, the left-hand force rule applies. All right, so up until now, we've been using the right-hand force rule, and all of our rules have been right-hand because I think it's less confusing if we just kind of stick with one convention. I just wanted to explain why in this particular animation, the force is working differently than you would expect, simply because this is a negative charge in question. And so it's the same type of rule, you just use your left hand instead, which means the thumb goes with path of the charge, fingers go with field, and your palm faces in the direction of force. That's the left-hand force rule, which applies to negative charges. Now, we're only going to use that in this particular animation, but for the rest of the video and really the rest of the year, we'll always be talking about right-hand rules and positive charges.
For example, the charges might be electrons in a piece of wire. Just moving a wire through a magnetic field makes a current try to flow. But the field of a bar magnet can be perpendicular at every point to a circular loop of wire. So, moving the loop creates a force that drives a current all the way around the loop. The current flows one way if the loop moves upward, and the other way if the loop moves downward. Of course, a current also flows if the loop stands still and the magnet moves. One way if the magnet moves downward, the other if the magnet moves upward. In fact, Faraday found that any method of changing the magnetic field through a circuit would make a current flow.
And that brings us to Faraday's original experiment. And in this experiment, he proved that a change in flux is what causes an induced current. Now, just to back up a tiny bit, if you think about it, a change in flux really just means the cutting of field lines. They're not two different situations, it's the same situation. A change in flux boils down to the cutting of field lines. And I'm going to show that in an animation shortly. We're going to see that they're the same. But what Faraday, what he proved in this experiment is that a change of flux causes a current. Now, how did he do that? If you close the switch in the primary circuit, what you do is you magnetize this solenoid down here. This is an electromagnet, and that sudden burst of magnetic field gets transmitted through the iron core, and that means that before the switch, whereas there was no magnetic flux through the secondary circuit, after the switch is closed, there is now a sudden magnetic flux through the secondary circuit. And so now that you have a sudden change in flux through the secondary circuit, you're going to get a momentary current induced in that circuit. And so a change in flux then, it causes an induced current. Now, Faraday formalized his law of induction in this way. An EMF, or electromotive force, is induced only when the magnetic flux through a loop changes with time. All right, so let's take a look at this diagram here. If I have a magnet stationary, the magnetic field lines, clearly there is some flux through this coil, but there's no change in flux because there's no motion. But once I introduce motion, as I can see down here, I've got this bar magnet moving to the right. Well, once I introduce motion, there's a change in flux, and I can see that the flux is increasing because these field lines are getting more and more dense as the magnet goes right. So increase in density of flux is an increase in flux. Now, what does this equation mean? Let's break it down. The epsilon just stands for EMF, or electromotive force, right? And this is measured in volts. Okay. Now, I know I've been talking about induced current, but current can only arise when there's an electromotive force, when there's a voltage. Current is caused by voltage. All right. So the way that he wrote it is he's expressing it in terms of the voltage that causes the current. So epsilon equals negative n delta phi over delta t. Phi is the symbol for flux. It makes sense, phi, flux. And t is time, obviously. Delta phi over delta t means the rate of change of flux. Just like you remember when we were doing mechanics, velocity, acceleration, displacement. Delta v over delta t was acceleration. Change in velocity over change in time, same concept. All right. So this is a rate of change of flux. N is the number of turns or number of loops through a coil. All right. So let's count this one over here. Has 1, 2, 3, 4, 5, 6. It looks like. Yeah, it looks like 6 loops. And so N would be 6. And then the negative just refers to whether it's a positive voltage or a negative voltage. So you can see here, if delta phi over delta t is positive, meaning that the flux is increasing, well then you have negative volts. And if the flux is decreasing, that would make delta phi over delta t negative. Negative times negative is positive, and you have positive volts. All right. Now, the important thing about Faraday's law of induction is that we see the induced EMF, which causes, of course, the induced current. This induced EMF is dependent on 2 main factors. How fast the flux is changing. And so the greater the flux, the greater the rate of change, or the smaller the time, the greater the rate of change. All right, both of those. But the rate of change of flux is a factor, and the number of turns in the conductor that cuts those field lines is a factor. Now, let's examine how the cutting of field lines is really equivalent to change in flux. This animation will help us to understand how the cutting of field lines relates to the rate of change of flux. All right, so we have the situation here of a bar magnet in the vicinity of a conductor coil, and we've seen this several times today. But let's take a look at this, and I want you, as we do this, to be looking at this spot where I have the mouse arrow, right at that spot on the coil. And I want you to notice as we do this that the flux changes. All right, so right now there's very little flux. There's only one field line through the coil. But as the north pole here gets closer to the coil, as we move the bar magnet left, these lines will get closer and closer together, which means the flux is denser. And therefore there's an increase of flux. So if we move the magnet left, we increase the flux. And then if we move the magnet right, we decrease the flux. Okay, so remember, take or keep looking at this point right here. This point. Here we go. All right, so flux is increasing, 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 decreasing, 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 increasing, 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 decreasing, decreasing, decreasing. All right. notice how as the flux was changing, these charges here in the coil were moving because a current was induced. All right. Now, what does the change in flux, or how does that relate to the cutting of lines? Well, look at that point I told you about, and let's watch it again. Cut, 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 cut. You see how the field line cuts? Cut, 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 cut. All right, every time I say cut, a field line is cutting through the conductor. And that it's the same as if the magnet were still and you had the coil moving around the magnetic field. All that matters is the relative motion between the two. It doesn't matter which one's stationary, which one's moving. But you can picture that if you move the coil instead, you're making the conductor cut through magnetic field lines, and that means that the right-hand force rule applies, like we saw at the very beginning of this video. This is the essence of electromagnetic induction. The cutting of field lines, which, as we can see in this little animation, is really equivalent to the change in magnetic flux. All right, so right here, if you look at the mouse arrow, we can see the precise moment in which the conductor is cutting a magnetic field line. And let's look at it one more time. Cut, 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 cut. All right, and every time it cuts, there's an induced current. Flux is increasing, increasing, increasing. Flux is decreasing, decreasing, decreasing. All right, so all that to just hammer home the point that change in magnetic flux is really equivalent to the cutting of magnetic field lines. All right, here's a more formal presentation of magnetic flux. So we have our conducting coil here. It has 6 turns, it looks like. 1, 2, 3, 4, 5, 6. 6 turns, so N is 6. This is a circular coil, and so there's a certain area, right? If there's a radius to that loop, well, we can just calculate the area, pi r squared. Now, area, we don't often think of area as a vector, but you can actually treat area as a vector in which the direction of the area vector is perpendicular to the plane of the area. And we can see that right here. Okay, this dotted line would be the direction of the area vector. And B, the solid blue lines, is the direction of the magnetic field. All right, so magnetic flux is the dot product of B and A. That just means that it's the magnitude of B times the magnitude of A times the cosine of the angle between them, cosine of theta. All right, this is the formal definition of magnetic flux. Phi, which is the symbol for flux, equals B cosine theta A, which is the same as BA cosine theta. And in vector math, if you've taken pre-calculus, you probably know this from the chapter on vectors. BA cosine theta is the dot product of B and A. All right, the unit of flux is the Weber, and a Weber is just a Tesla times a meter squared. Now, Faraday's law of induction is very useful. I'm going to show you a couple of devices now, and then we'll finish the video with its most important use. This is a guitar pickup, and in an electric guitar, the way it works is you have a magnetized portion of the string, and when you strum the string, this oscillates back and forth, okay, like my mouse arrow is doing right now. Well, an oscillation of this magnet back and forth is equivalent to a rapid changing of flux, changing of magnetic flux, through this permanent magnet. okay? Because this magnetized portion of the string interacts with the magnetic field of this permanent magnet. And what you get is a rapid changing of magnetic flux through this coil. Well, rapid changing of magnetic flux equivalent to rapid cutting of magnetic field lines. And what do you get? You get an induced current. Now, since this is going back and forth, right? Well, that means this current is going back and forth. But what picks up on that? The amplifier. Those currents are transmitted to the amplifier, which then converts them into sound. And so what you have is you have tiny electric currents induced by a magnetized guitar string. And these tiny electric currents induced by the magnetized guitar string are what you're hearing in the amplifier. The amplifier simply converts those signals into sounds. And so naturally we can get some very loud sounds and even effects like distortion and reverb, settings on the amplifier, because of the way that an electric guitar uses electromagnetic induction. It also is the same with a microphone. Okay, so a microphone is really like the opposite of a speaker. All right, so if you have an amplifier hooked up to an electric guitar and a speaker, well, that speaker is working like this microphone in reverse. Okay, but first let's talk about how the microphone works. All right, so when the singer sings into the microphone, here's what happens. The microphone has a sensitive thin plastic diaphragm which vibrates in response to the vibrations of air, which is sound. All right, and so this vibration of the diaphragm then, since that diaphragm is attached to a coil, what we have is a rapid oscillation of a coil in the presence of a stationary bar magnet. And what does that give you? It gives you induced currents. And those induced currents then get transferred to an amplifier, which makes the sounds loud. Now, I mentioned a little bit earlier that this is just a speaker in reverse. Well, sure enough, that's what happens. If you want to picture this as a loudspeaker, well, if you want to make sound instead of pick up sound, you just transfer currents to the diaphragm, and the diaphragm will move back and forth in response to those currents, and that produces sound. Okay, so guitar pickups, microphones, speakers, these are all applications of Faraday's law of induction. Another one is transformers. So a transformer is used to change voltage in an alternating current from one value to another. All right, this is actually very important for household electronics or electric circuits, because what happens is your power line is at a high voltage, and then when it arrives to your house, it's got to go through a transformer to step it down to a lower voltage, namely 120 volts for the standard American household. Okay, and so what you get is you have low current, high voltage in the power lines, and the transformer converts that into a lower voltage, high current, which is what you need in your house, okay, in your house circuits. Now notice this little symbol. This little symbol here, we haven't encountered that until now. This is the symbol for alternating current. Alternating current. Right? I'm going to talk a little bit more about this, but alternating current is really the reason why transformers work. All right, let's talk a little bit more about this diagram. Okay, so in my primary circuit, I've got a bunch of loops in the coil, and in my secondary circuit, I have, as I can see here, fewer. Well, it turns out that the high voltage is proportional to the high number of turns, and the low voltage is proportional to the low number of turns. That's what N stands for. Okay, and the magnetic flux is concentrated in this iron core, just like Faraday's original experiment. It's very similar, this setup. And so the changes in flux through the primary coil get transmitted as changes in flux through the secondary coil. All right, so what is the math behind transformers? Let's take a look at that. All right, so here's the transformer equation. And the way to understand this is, I think it's best to first understand it in this way. So I'm going to rewrite these equations as Vp over Np equals Vs over Ns. Now, this is a little more intuitive for us if we look at the picture. Okay, so we're going to look at the picture again. All right, Vp over Np equals Vs over Ns. Let's take a look at this picture here, right? So high voltage, a high number of turns, right? High V, high N. And that becomes low V, low N. So the ratios must be the same. So Vp over Vs equals Np over Ns. All right, all we did is we swapped these two here, the Np and the Vs, but we know from algebra that that's just the same thing. Algebraically, it's the same thing. All right, so this is really just a rewriting of the proportion. And the reason this is convenient is because we can see that the ratio of primary voltage to secondary voltage is the same as the ratio of primary number of turns to secondary number of turns. Now, in transformers, that makes it easy to calculate the input voltage and output voltage. And you can step it up or step it down to whatever voltage is needed. Now, the power in both circuits must be the same. Therefore, if the voltage is lower, the current must be higher. Okay, let's take a look at that, just to prove that to ourselves. So, P equals IV. We've been seeing this equation over and over. As you know, P equals IV, P equals I squared R, and V equals IR are extremely simple but important equations in electricity. And they keep showing up. So P equals IV, power in watts, equals current in amps, times the voltage in volts. All right, well, if this is true, and you know, you can't increase power, the input power must be the same as the output power, just as the power of a sound close to an explosion is the same as the power of a sound far from explosion, even though the intensities are different. All right, power doesn't change, the watts are the same. And so we can clearly see that we could rewrite this as P S equals I S Vs. Now, if it's true that PS, and these are pretty bad letters here, but you can read them. If it's true that PS equals ISVS, well, then it also must be true that PP equals, you guessed it, IPVP. PP equals IPVP. That sounds weird when you say it fast. PP equals IPVP. All right, so if PS equals PP, then it must be true that ISVS equals IPVP. And if that's true, then algebraically this is the same. IS over IP equals VP over VS equals NP over NS. And there we have the ratios, all the ratios we need to do step up or step down transformers to get the proper current and voltage. And as I said earlier, the beauty of this is that over the power lines you have high voltage, low current. That ends up giving you fewer losses when you transmit power over long distances. And you get fewer losses in power that way, so that more of it will come from the power plant to your actual house. However, when it gets to your house, what you want is a lower voltage but a higher current, so that it can be useful for your household appliances. Here in this arrangement I have a battery hooked up to a coil with 4 turns, and I have a light bulb hooked up to a coil that has 2 turns. Now if you look closely, you'll see, well, I've got magnetic field here because this is an electromagnet. This is a solenoid, and the current is producing a magnetic field. But I've got no current in the smaller circuit, or the circuit that has fewer loops. And that's because there's no cutting of field lines. There's no changing of flux. Now, once of course I move this back and forth, notice that I'm getting the cutting of field lines, and I'm getting that change in flux. And it's the change in flux through the secondary coil that causes the bulb to light. Alright, well, this is not practical for transformers because you have to put a lot of work into moving the magnet back and forth, the electromagnet. And that's the beauty of alternating current, which is our household supply. Alternating current is just back and forth. Alright, so I'm going to change the current source to AC over here. And I've got a meter showing my AC current supply. Now notice what happens. I'm going to turn this up a bit. And I'll turn this up a bit too. Alright, so we can see what's going on here. We see that on the left, this coil has 4 turns, so that its N is 4. It's got a higher voltage. But over here, N is 2, and we have a lower voltage. We can see that. We can see that in 2 ways. We can see that because these electrons are moving back and forth more slowly, and also not as much. So there's going to be less voltage here. All right. Now this is kind of an interesting thing because this is exactly how our household transformers work. So power comes in from the power lines, and then it has to hit a transformer in order for that high voltage and low current to be stepped down to a lower voltage, 120, and a higher current. All right, so this is a simplified schematic of how a typical AC transformer would work, and it's all just based on the fact that the flux is constantly changing. Okay, take a look at, right now I'm pointing at one of the magnetic field little compass indicators. Notice how it's switching back and forth, and it's switching back and forth precisely because the current in the primary coil is going back and forth. Alright, so if the current goes in one direction, the magnetic field goes in one direction, and if the current goes in the other, magnetic field goes in the other. Well, that flipping back and forth of directions is equivalent to a change in flux. It's a change in flux, and that's what induces the current in the secondary coil. And of course, because the number of loops is different in the coils, we can get a different voltage. Let's take a look at perhaps the most important application of Faraday's law, and that is the electric generator. So again, this is a very simple generator to generate AC current, and in this situation what we can see is that there's no magnetic flux. I'll show the field over here. Okay, so you can see the field, but the field's not moving, so flux is not changing, and therefore there's no current. Now, if I can get the magnet to move, then of course I will be able to get changes in flux, which will lead to an induced current in the coil. All right, let's see this in action. I'm going to turn on the water, and we can already see what's going on. All right, so I am using this water wheel to turn the bar magnet. As I do so, I'm causing the magnetic field to change. And since the magnetic field is changing, that means the flux through this coil is changing, and a changing flux is what gives us an induced current. All right, let's see what effect there will be if we increase the number of loops in the coil. Well, notice that when I go to 3, I get a brighter light. And if I go back to 2, you can see there's a little less. If I go to 1, I can see that there is less. All right, so this goes back to Faraday's law of the electromotive force equals negative N delta phi over delta T. And we can see that N is a factor, because the greater N is, the greater the EMF, and the lower N is, the lower the EMF. All right, well, N is not the only factor. I'm going to bring this back up to 3 here. Another factor is the rate of change of flux. Okay, so if the flux changes slowly, you get less EMF. If the flux changes rapidly, you get more EMF. Okay, let's see what happens if we turn on the water more. Well, right away we can see that the flux is changing more rapidly. Because of that, we have a greater induced EMF. If I put it way up high, 100 RPM, this is where I get the brightest light. By the way, just a little side note. Let's take a look at this. You'll see this is I'm inducing an AC current, and because of that, the light's flickering. So you might ask, well, if my household supply is AC, then why don't my lights flicker? And that's a good question. Well, it comes down to the fact that the hertz, or the frequency of the alternating current, is 60. So that means 60 times per second it goes back and forth. Now, if a light bulb is flickering 60 times per second, that's so fast. It's so fast that your eyes can't distinguish that the light is flickering, which is kind of an interesting thing. Our lights don't appear to flicker, but in reality they are. It's just that our eyes can't distinguish the flicker because it happens so fast. All right, let's talk a little bit more about generators and motors. So, if we have an electric motor, and we studied that in the last chapter, it gets electrical input, and then because of the current that causes in the armature, a torque is caused, and that torque turns the armature around in the magnetic field. Okay, we already know the principle. We know the principle of the electric motors and how they work. All right. Notice that the cool thing about here is I don't have a commutator. I've got brushes, of course, but I don't have a commutator like we had in the direct current motor. And that's because AC motors like this one, they don't need commutators. Most of your appliances have AC motors inside. And so what you'll get is that the current will switch direction, but in sync with the rotation, and so you're getting a constant rotation. It's not like the AC is causing the motor to go back and forth. No, but because it's in sync, thanks to the metal slip rings, we're getting a constant spin in one direction. All right, but the important thing here is that we have electrical input, right? But our output is mechanical. This is why we have electric motors, to do work. We feed them electricity, and what they do is they give work. Well, an electric generator is really just the same thing, except that here the input is mechanical and the output is electrical. Notice how they're the same. It's the same setup. See, if you look at these two slides, see it's the same setup with the slip rings and brushes, okay, the armature rotating in the permanent magnetic field. Same setup. All right, but what we're doing here is we have the mechanical input, and what we're getting is we're getting AC output. Okay, all right. So the cool thing about this is that it's really the same setup, but we can see that generators and motors are just different sides of the same coin. It's really just the exchange or the interchange of electrical energy and mechanical energy. Now, generators are very useful. They are the heart of every power plant. You know, you flip any switch in your home, turn on any electronic device in your home, and you are benefiting from the electric generator. And ultimately, you are benefiting from Michael Faraday's discovery and careful, meticulous work to figure out what causes electromagnetic induction and to figure out how it can be used. In fact, Faraday also created the first generator. So he created the first electric motor, the first transformer, and the first electric generator. Let's take a look at the working of an electric generator. And what we see here, if we look at the graphs, is we can see the relationship between flux and current. Okay, so I'm going to play this again, but pausing at key points. Alright, so let's look at this. And first, before I even play, let's see this opening frame here. Okay, so the loop, the conducting loop, is right now parallel, its plane is parallel to the magnetic field, which means there is zero flux. And that's why in this graph here we can see that flux is at 0. Okay. Now the current is at a high. That's only because of the position that the loop had before. Okay. So let's watch this first part. Now I pause it again right when this loop is perpendicular to the field, and there we can see that flux is at a high. Okay, but notice that field lines are not being cut. No, field lines are going straight through. They're not being cut, and that's why current is at 0. Okay, let's advance a little bit more. Okay, now we see that it's parallel again. Okay, which means 0 flux. However, the loop just got done cutting a whole bunch of field lines, right? There was just finished a whole process of flux changing, and that's why this current's magnitude is high. Notice though that it's been flipped. It went from positive to 0 to negative, and then it goes to 0 to positive again. Alternating current is sinusoidal. It looks like a sine wave, or in this case, it looks more like a cosine wave. But we call that type of motion sinusoidal in a graph. And let's look at this just a little bit more. Now, when I stop it there, same deal. Maximum flux, right? Here, though, we're calling it a negative flux, just because it's in the other direction. But the magnitude is at a max, and the current, since no lines are being cut, is at 0. We're going to talk about Lenz's law. So Lenz's law is named after, you guessed it, a guy named Lenz. Actually, his name was Heinrich Lenz, and he was a Russian physicist of German ancestry, a contemporary of Faraday. In fact, Faraday published his results in 1831 after a decade of meticulous study in electromagnetism, and that's precisely the year that Lenz began studying electromagnetism. He took an interest in it in Faraday's publication. All right, so Lenz's law then basically adds to our understanding of electromagnetic induction, because what we know is that a change in magnetic flux induces a current. Lenz's law tells us about the direction of that current. So an induced current always flows in a direction that opposes the change that caused it. So think of nature as, nature likes to maintain the status quo when it can. Go back to our study of mechanics and Newton's first law. If something's at rest, that's how it wants to stay. If something's in motion, that's how it wants to stay. Nature tends to resist change, at least in physics, right? Change gets resisted, even though change happens, of course, but it gets resisted at its very basic level. So we've got the law of inertia in mechanics, resistance to changes in motion. Well, in electromagnetism, we have Lenz's law, which shows that nature likes to keep the status quo, even though it can't. It kind of tries to in a desperate attempt to maintain a steady state. So let's take a look at that in terms of these two diagrams down here. All right, so over here to the left, I have a bar magnet moving right. And we can see that as this bar magnet moves to the right, the flux through the loop will increase. The flux through the loop will increase. Now, nature is resisting the change. It's resisting the increase of flux. And so what it tries to do then is the induced current sets up a magnetic field. We can see with these field lines here. And that magnetic field opposes the increase in flux. Okay, so look at this bar magnet. It's kind of adding all these new north lines of field into the loop. Well, the loop is trying to resist all those north lines by opposing them. And we can look at this loop here. I'm kind of tracing it now with the mouse arrow. And I'm tracing it around and around in the direction that the current would go. Well, using the right-hand loop rule, the fingers wrap around the direction of the current, and thumb points in magnetic north, which is right here. Okay, so what's happening is it's trying to resist the change. The loop sets up a magnetic field that opposes the very magnetic field that caused the current in the first place. Let's look at this situation over here. Okay, this situation over here has a bar magnet that's moving to the left. And it's moving to the left, which means that the flux from the bar magnet is decreasing through this loop. We can see these north lines are being taken away. The north lines are receding away from the loop. And so what does nature try to do? Well, induce a current in a direction such that it sets up its own magnetic field that desperately tries to replace the magnetic flux that the moving bar magnet has deprived it of. Okay, it's again a desperate attempt to resist a change in the status quo. All right. Now notice how these are two different current directions based on two different directions of the change in flux. When flux is increasing, current goes one way. When flux is decreasing, current goes the other way. Let's take a look at this simple circuit here. We have conducting wires, and they are connected to a conducting rod. the rod can slide up and down, but as it slides up and down, it's always in contact with the vertical wires, and so the circuit's never broken. Now, when everything's just standing still, there's no induced current, there will be no light. But if we suddenly allow this conducting rod to fall, if we allow gravity to make it fall, here's what happens. Notice that this conducting loop is in the presence of a uniform magnetic field, B. And the field lines, indicated by these symbols, are coming out of the screen, or out of the page, however you want to think of it. That's what these dots mean. It means that the magnetic field is coming out of the screen. All right, that means there's a certain amount of flux through this loop. And I'm tracing out the loop with a mouse arrow right now. It's got kind of a square shape, but it's a loop nonetheless with an area that can be calculated if you know the sides, right? We know the lengths, but aside from that quantitative area, what matters is just the fact that you understand that this is an area. Okay, well, it's an area, there's a magnetic field, therefore there's magnetic flux. However, there's no change in flux unless this conducting rod is allowed to fall. All right, so let's say we do allow it to fall. That introduces a change in flux, and as we already know, changes in flux, which are tantamount to charges cutting through magnetic field lines, induces a current. Now the current goes this way. Let's try to understand why it goes this way. First, we're going to understand why it goes this way in terms of the right-hand force rule, and then we'll understand it in terms of Lenz's law. And as you might expect, they don't oppose each other. In fact, they have it's the same exact phenomenon, just explained in two different ways. First, let's talk about this current I in terms of the right-hand force rule. All right, so if I put my right hand up, I line up the fingers with the magnetic field. So notice how the fingers are coming out of the screen, just like the field. The thumb is going in the direction of the path of the charges that the conducting rod contains. So think of the conducting rod as containing all these charges. And here we're looking at them as positive charges because that's how conventional current is rendered. Okay. Well, all right. Positive charges then, since the whole rod is moving down, well, naturally every single positive charge in the rod is moving down. And so the thumb lines up with that path. And that leaves the palm to face the direction of the force that each of these charges experiences. And notice they're all experiencing a leftward force, which means the current will be leftward. And so if the current starts leftward up in this rod, well, to complete the circuit, that becomes counterclockwise. All right, so we're going to have a counterclockwise current thanks to the right-hand force rule. All right, now this is the same situation, but we have to remember that two things are going on here, okay? The first thing, as I already showed you, is we get the current induced. But once the current is induced, well, that means that now these charges are moving to the left, and since those charges now have a path, they're going to have the right-hand force rule applied to them as well, but regarding their leftward velocity now. Okay, back here we were talking about the charge's downward velocity. That's why the thumb was going down. But now that the charges are going left as well as down, we have to take into account this leftward motion. And the right-hand force rule will apply to that as well. Let's see how. Okay, We've got the fingers lined up with the magnetic field. Fingers are coming out of the screen, just like the field is. We've got the thumb lined up with the leftward path. Keep in mind, these charges are moving both down and left, but now we're only thinking about the leftward component, and that leaves the palm facing up. And the palm facing up means the force is going up. That means that this force opposes the force of gravity, which is causing the rod to fall in the first place. All right? Nature is again resisting the change. The rod falling causes a change in flux. And so how do we resist that? Well, we have this upward force to put the brakes on, to put the brakes on the downward fall. And we can see that upward force illustrated with the right-hand force rule. Okay, so far we've talked about this situation and the direction of I solely in terms of the right-hand force rules. Well, now we're going to talk about it in terms of Lenz's law. Okay, here's the conducting rod falling down. Because of the right-hand force rule, the brakes are being put on, slowing the fall. Okay, but let's take a look at this from the perspective of flux. Okay, these lighter gray dots here, or bluish gray dots, this is the permanent magnetic field coming out of the screen. All right, now if this rod is falling, that means this area is decreasing. And since this area is decreasing, the flux is decreasing. Now, nature is trying to make up for that flux that it's losing. And so it now sets up its own magnetic field. Notice that I'm tracing around and around this loop. I'm tracing around and around. I have a current going around and around counterclockwise. Well, any current in a loop, as we already know, creates its own magnetic field. And that magnetic field, we know from the right-hand loop rule. And so let's look at this in terms of the right-hand loop rule. Okay, in the right-hand loop rule, the fingers curl around in the direction of the current. Notice how the fingers are curling counterclockwise. That leaves the thumb pointing in the direction of magnetic north for this magnetic field produced by the current. Now notice this magnetic north coming out of the screen, okay, this lines up with these magnetic field vectors that are due to the current I. All right, so these magnetic field vectors are coming out of the screen in the desperate attempt to replace those lines coming out of the screen that are being lost by the decrease in area. Okay, so Lenz's law coincides with the right-hand force rule, just as change in flux coincides with the cutting of field lines. They're just different ways of understanding the same phenomenon. Lenz's law then determines the direction of an induced current. Now, the main application for this is we can create brakes. This is actually really neat because we can create brakes that can slow a conductor down without even touching the conductor. And that's kind of it's cleaner than, traditional brakes that use brake pads or friction against the moving thing, and there's a lot of heat, and then you got to replace the pads and all that. Well, you can actually set up a braking system to slow conductors down, and you can do that without any contact. Now, let's take a look at how that works. This strip here, or this sheet of metal, we're going to call this sheet of metal a bulk conductor, which means it's just a big old conductor. It doesn't have any particular special shape. It can be square, circle, it can be a rhomboid, a trapezoid, doesn't matter. It can be odd shaped. What matters is that it's a sheet of conducting material.
All right, let's look at this magnetic field. We've got a small magnetic field here. It's small, but it's pretty compact, and it's uniform. And the field lines are coming directly out of the screen again. And let's examine what's going to happen to the sheet of metal as it falls down. So picture this sheet of metal has fallen from the sky. Suddenly it comes down here, right, and continues to go down and then falls all the way to the ground. Well, while it happens to be falling through this magnetic field, nature puts the brakes on. And nature puts the brakes on according to Lenz's law. Okay, let's take a look at this. This is called an eddy current, named after, I don't know if you've ever been to, been fly fishing or fished in a river, but I'm going to draw a little shoreline here. Okay. All right, let's suppose this is a river. Okay, if this is a river, current comes down this way, right? This is the stream, liquid coming down here, right? Moves down here, current's going down here. But what happens at this spot is you get a little curling around, okay, because of the shape of the bank in that spot. And you get that little curling around because the current is coming straight down here, but it's curling around here, and this is called an eddy pool. These are eddies, and this is a little eddy pool. Sometimes fish hang out there because the loop brings them food to eat. But anyway, that's where the term comes from. Eddy. All right, so this is an eddy current, which is a temporary current. It's not usually a perfect circle. It can just be any random closed shape. It could look like this for all you care. It doesn't matter because on a microscopic level, right, all that matters is that electrons are going around in a loop, but they're not necessarily following a circle. All right, but for simplicity, we're looking at this as a circle. Okay, so sheet of metal is falling down. It's falling through a magnetic field. That means that through every little part of the conductor that goes through the field, that every little part is experiencing a change in flux. If we zero in on this particular part, okay, here's our eddy current. It's going around in this direction. Why? Well, Lenz's law tells us that as this sheet of metal goes down, okay, as this sheet of metal goes down, well, that means this whole green circle is going down. And if this whole green circle is going down, then it's going to lose this flux. And right now, that flux consists of just these two field lines. But as the whole thing falls, green circle and all, eddy current and all, the amount of flux through this eddy current is decreasing. So how does nature try to compensate? Well, it sets up a current, and we can understand the direction of this eddy current, this counterclockwise direction, by using the right-hand loop rule again. Notice how we curl our fingers in the direction of the current, and that leaves the thumb pointing in the direction of magnetic north. All right, so just as this eddy current and the whole conductor are falling out of the magnetic field, thus losing flux, we can see that the induced current, this eddy current, then sets up its own magnetic field to try to oppose that loss of flux, and it creates flux of its own. Now, another way to understand the braking caused by eddy current, right, the fact that it's acting as brakes, we can look at it in terms of the right-hand force rule. And here we're looking at just the top part of the eddy current, right? And if you look at the top part of the eddy current, and this will apply to the other parts of the curve as well, insofar as those parts of the curve have some vertical components of the force, because these parts of the curve also have some horizontal components of velocity, the path of the charges, right? But for simplicity, we're just going to look at what I'm circling now, which is that that top arrow there. And let's say we're looking at some charges at that top arrow. Well, at that particular spot, they're moving left. Notice that the path of those charges lines up with the thumb. The magnetic field lines up with the fingers, and that leaves the palm facing upward in the direction of the force of braking. And so that upward force is slowing down the fall of this conductor through the magnetic field, all thanks to Lenz's law. This kind of braking is actually used commonly in exercise bikes. If you've ever gone to a gym and seen the cardio machines, you've probably seen exercise bikes. And they have variable resistance. You can make them hard to pedal or easy to pedal. But that resistance is often controlled by magnets, and you can bring the magnets closer to the wheel or farther from the wheel. You can expose more area of the magnet to the wheel or less. These are ways to control the resistance, but it's all based on the same principle of eddy current braking, using eddy currents as brakes. Let's finish with a cool demo of eddy current braking.
This is an ordinary pendulum, but it has a piece of copper at the end. And when it swings, the piece of copper swings between the poles of an electromagnet. But the magnet is not turned on right now. If the magnet were turned on, imagine what would happen. The piece of copper would swing into the magnetic field. Because it's swinging into the magnetic field, then by electromagnetic induction, electric currents would be induced to run around in the copper. Now, whenever currents run around in a piece of metal, that causes heating. And so there would be heating, and that means that energy is being lost from somewhere. But where does the energy come from? Well, the only place it can come from is the swinging of the pendulum. So the pendulum should actually slow down if I turn on the magnet, which I can do by closing this switch. So here's what I'll do. I'll get the pendulum swinging again, and you sort of get the rhythm of the pendulum swinging back and forth. And then when I close the switch, you'll actually be able to detect that the pendulum slowed down. Okay, so here we go. I'll get it swinging again. Watch it. I'm going to close the switch right now. Watch this. There. Did you notice that?